Hello everyone, welcome to my channel. So I've started offering specialized one-on-one classes in physics, chemistry and math EE for both SL and HL. So for the rates, the standard rate is $35 per hour. If you book like 5 or more classes, it'll be 30, and if you book 10 or more, it'll be 25. So these courses will be tailored to your needs. Whatever you want to learn, we can discuss in these classes. Please don't hesitate to reach out to me. You can contact me at this given email, and yeah, to schedule your class. So with this, let's get started with this paper. Thank you. My channel. Today we'll be solving paper 2 of November 2025 attempt of time zone 1. So let's get started with the first question. So phosphorus is an element which is an essential part of the biological molecules involved in both respiration and photosynthesis, of course. Draw the orbital diagram of phosphorus atom in ground state by adding, filling, and labeling orbitals using section 7 of the data booklet. Quickly check section 7. Section 7 is probably the periodic table, yeah. So phosphorus is an atomic number of 15, so it has 15 electrons, yeah. If we write the electronic configuration, it will be 1s2, 2s2, 2p6, 3s2, 3p3, 15 electrons done. Yeah. They have shown 1s and 2s. So let's just fill in electrons, 2 electrons in 1s, 2 electrons in 2s. Yeah. Then after 2s, 2p orbital, 2p subshell will be filled. So 2p, we have 6 electrons. So 1, 2, 3, 4, 5, 6. After 2p, 3s will be filled. Yeah. So 2 electrons in 3s. After 3s, 3p will be filled. 3 electrons in 3p. So we'll fill like singly fill each of the orbitals. So this is the orbital diagram of the phosphorus atom. Yeah. Now we have to sketch the shapes of two different orbital types at the second energy level. Second energy level, right? So we can we have to draw 2s and 2p. These two are like subshells basically. For 2s, if I want to draw it, let's say this is x. Yeah, this is y, and this is z. These are the three axes. 2s orbital will be a spherical orbital, right? So it will just be a sphere like this. Yeah. This will be your 2s orbital. Now for 2p, we have three options. Either you can draw 2px or 2py or 2pz, right? You just have to align the dumbbell in that specific axis, yeah? So we can draw 2px. This is the 2px subshell. Done, that's it. Next one, we have to explain why ionization energy decreases as we descend group 15 from nitrogen to bismuth. Yeah. So basically, as we go down any group, what happens is our nuclear charge, number of proton increases. Yeah. But the added electron shells, right? So more and more shells will be added. So electrons will be further apart from the nucleus. So firstly, the force of attraction won't be that much. Secondly, you'll have more inner electrons. Because of that, the outer electrons will experience more repulsive force. So there'll be an increased shielding effect. Yeah. So because of that, when you move down the group, what happens is the net nuclear attraction decreases. As a result, you need lesser energy to remove the electron. Yeah. We write it down. And the first ionization energy decreases down to 15 because although nuclear charge increases, the added electron shells increased shielding and a larger atomic radii. This reduces the effective nuclear attraction on the valence electron So less energy is needed to remove it. That's it. Next, 7.75 grams of phosphorus was combusted in a limited supply of oxygen. The mass of oxide produced was 13.75. We have to calculate the number of atoms in 7.75 grams of phosphorus using section 2 and 7. So you have to just use a periodic table and the formula. So moles of phosphorus will be mass over molar mass. Mass of phosphorus is 7.75. Molar mass, if you check the periodic table, find it as 30.97. Divide them, you'll get 0.2502. This is the moles. So number of atoms, this will be moles times the Avogadro's number. So 0.2502 times 6.02 times 10 to the power of 23. Simplify this, I'll get 1.51 times 10 to the power of 23. Next, you have to determine the empirical formula of the oxide form. To show, show our working in section 7 again, we have to use the periodic table. So it's an oxide. So moles of phosphorus you have already found 0.2502. You have to find the mass and moles of oxygen. So mass of oxygen will be 13.75 minus the mass of phosphorus, which is 7.75. Yeah, we have 6.00 grams of oxygen. You have to find the moles of oxygen, which is 6 divided by molar mass of oxygen is 16. So it gets 0.375 moles of oxygen. Then you have to take the simplest whole number ratio between moles of phosphorus and moles of oxygen. 0.2502 is to 0.375. We'll divide both with the smaller number, which is moles of phosphorus, and divide both with 0.2502. This becomes 1, and the other one will be 1.5. Then we can just multiply both sides with 2 to make it whole numbers, so 2 is to 3. The empirical formula, this would be P2O3. That's the answer to part 2. Now, the molecular mass is given. We have to find the molecular formula. So basically, we have to find N, which is the molecular mass divided by the empirical formula mass. Yeah. Molecular mass is 219.88. Empirical formula mass, you have P2O3, 2 times molar mass of phosphorus plus 3 times molar mass of oxygen. You do this, you get 2. Yeah. So the molecular formula, this would be P2O3 whole twice, sorry, which will become P4O6. That's the answer to part 3. Next, this oxide of phosphorus is a melting point of 296.9. Outline with the reference of structure and bonding reason why melting point of this oxide is low. Okay, good. So we have to know that P4O6 is a non-polar molecule, right? It's a non-polar simple covalent molecule. Yeah. As it's non-polar, the only intermolecular force that will exist between two molecules of P4O6 will be weak London dispersion forces, right? And that is the reason why its melting point is low. So P4O6 is a non-polar molecule. I can say non-polar, simple covalent molecule. The only intermolecular force of attraction is weak London dispersion forces. And hence the melting point is low. Done. Next, we have to describe the nature of bond between oxygen and phosphorus using section 9 and 17. Section 9 gives us the electronegativity values. Section 17 is the bonding triangle. So we need to find the electronegativity of phosphorus and oxygen from section 9. Then electronegativity of oxygen. Section 9, it's here. Phosphorus will be 2.2, oxygen is 3.4. Okay. Yeah. Now, for bonding triangle in section 17, we need two things. We need the difference and we need the average. Yeah. So delta chi, this will be mod 2.2 minus 3.4. This will be 1.2. And then average, right? This will be 3.4 plus 2.2 divided by 2, which is 2.8. Yeah. The delta x, I mean, difference is 1.2, average is 2.8. We need to find that. So 2.2 and maybe I'll just remove this. Difference will be 1.2. 1.2 somewhere here along this line. Okay. And then the other one will be 2.8. 2.8 somewhere here. Okay, I got shifted a little bit. Never mind, this is the line. This point, this is the point. So it lies in the polar covalent section here. So let's say the bonding triangle, PO bond is polar covalent. Next, another compound of phosphorus is phosphine, which forms phosphonium ion pH4. It's a type of bond present in pH4 plus, right? So yeah, and explain how these bonds are formed. So basically, phosphine looks like this. Yeah, it has one lone pair. So basically, when an H plus comes near it, what happens is it donates its lone pair to this H plus. As a result, the pH4 plus compound looks like this. So there are three covalent bonds, yeah, and there is one dative covalent bond. So you can write the answer in this way: the phosphonium ion pH4 plus contains four polar covalent pH bonds. Three of these bonds are formed by paired electrons between phosphorus and hydrogen. And the fourth bond is a dative covalent bond where the lone pair on phosphorus is donated to the H plus sign. Done. Next, phosphorus trichloride, PCl3, is a common compound of phosphorus, Lewis formula of PCl3. Pretty straightforward, but we can do it my way. We find the number of valence electrons, the total number of valence electrons. Phosphorus and 5 and each chlorine will have 7. It will be 26. So if you want to find the number of electron pairs, you'll just divide it with 2. That's 13. So you have 13 electron pairs. So PCl, you will use 3 single bonds. Okay, that means 3 electron pairs will be gone to connect the compounds. Now, using the 10 electron pairs left, you'll first complete the octet of the outer electrons. I mean, outer atom, sorry. So 9 electron pairs will go away. 1 is left. So you see, phosphorus, octet of phosphorus is not complete. 6 electrons requires 2 more. Just place the last electron pair here. This is the Lewis formula of PCl3. Next question. Nitrous oxide, HNO2 and HCl are both inorganic acids, of course. 0.01 mole per dm cube solution of HNO3 has a pH of 2.63, while HCl, the same concentration, has a pH of 2. You have to explain the difference in pH. So HCl is a strong acid, HNO2 is a weak acid, right? So HCl dissociates completely. All of HCl molecules will dissociate to form H plus and Cl minus. Yeah. So it will have a higher H plus ion concentration. As a result, it will have a lower pH. HNO2 will not dissociate 100%. Yeah. What happens is only a few of the molecules will dissociate. So it will have a lesser concentration of H plus as compared to HCl. Yeah. And that's why exactly its pH will be higher. So let's write it down. HCl is a strong acid and it fully dissociates in water, producing a high concentration of H plus ions and hence giving a lower pH. HNO2 is a weak acid and only partially dissociates, which produces fewer H plus ions. So its pH is higher. Yeah. And describe what would be observed if an excess magnesium was added to equal volumes of the same concentration of nitrous and hydrochloric acids. So when we add Mg, the reaction is straightforward, right? Mg will react with the acid. So there will be a salt of magnesium and hydrogen gas will be produced. Right? But thing is, HCl is a stronger acid, right? So it will react more more vigorously with magnesium, while HNO2 is a weak acid. It will react less vigorously. So that's it. Put and produce hydrogen gas and a salt of magnesium. However, the reaction is faster and more vigorous with HCl, while it's slower and less vigorous with O2. That's it. So a solution of nitrous acid contains two conjugate acid-base pairs. Yeah, state the formula of conjugate acid and conjugate base in each pair. So if you're talking about a solution of HNO2, right? So you have HNO2 and water. So first, HNO2 can act as the acid. So conjugate acid is HNO2, conjugate base is NO2 minus. In the other case, you have water, right? Water with any HNO2 will behave like a base. Yeah. So your base will be H2O, while the conjugate acid will be H3O plus because H2O will accept the H plus from HNO2. Yeah. Next, we have to find the oxidation state of nitrogen in HNO2. So take nitrogen as X. Hydrogen is +1, oxygen is -2. This will be 0. So X minus 3 is 0. X is +3. Oxidation state of nitrogen in HNO2 is +3. Moving on to the next part. Picric acid, carbolic acid, and aspirin are trivial names of chemical substances. And they cause misunderstanding when communicating information internationally. So you have to outline how modern chemists have improved communication when naming chemical substances. So modern chemists now use IUPAC nomenclature, right? So the main thing about IUPAC nomenclature is the naming is based on the structure. So every organic structure, every different organic structure will have a different name, right? There is less chance of any confusion now. So if I want to write it down, this modern chemists use the IUPAC system, which gives every organic compound a unique name based on its molecular structure. This provides a standardized and internationally recognized names, reducing confusion created by different trivial names. So that's it about B part 1. Now coming to B2, the molecule of aspirin contains an ester functional group, right? So this is the ester group. Okay. Now we have to state the names of other two functional group. This functional group is carboxylic acid, or we can call it carboxyl. And this is a benzene ring, so just call it benzene. The other two functional groups are carboxyl and benzene. That's it. Now, so this is ethyl ethanoate, which is another ester. We have to deduce the structure and name for a functional group isomer of ethyl ethanoate. So ethyl ethanoate, if I follow the structure, it's CH3. So I'll just draw the displayed formula. CO2, so C double bond O, single bond O, CH2, CH3. This is ethyl ethanoate. Now, functional group isomer of any ester is a carboxylic acid. So here it's a carboxylic acid of 4 carbon atoms. Okay, 4 carbon atoms is butanoic acid. Okay. Done. Next, a catalyst which usually contains sulfuric acid, a catalyst usually concentrated sulfuric acid is used to manufacture this ester. Explain the action of catalyst. So catalyst lowers the activation energy of a reaction by providing an alternative reaction pathway. Yeah. So 2 markers, you have to write it in a little different fashion. So we can write it like this: the catalyst lowers the activation energy by providing an alternative reaction pathway, allowing more effective collisions per unit time and increasing the rate of the reaction without being consumed. Next, ethyl ethanoate can be produced by the reaction of ethanol with ethanoic acid. Both reactants can be synthesized from ethane through a series of reactions. So ethane becomes chloroethane, right? The first step in this reaction initiation is given by this reaction. So Cl2 breaks down into 2 chlorine free radicals. Essential condition for this reaction. So like, yeah, you have to put ultraviolet, right? Okay, or ultraviolet radiation. So ultraviolet radiation is required to initiate the homolytic fission of Cl2. Next, deduced two propagation steps and one termination step for this reaction. Okay, propagation step is when this chlorine free radical reacts with the ethane molecule. Yeah. So this is your chlorine free radical. This is like, these are the propagation steps. The first propagation step, chlorine free radical react with the ethane molecule. What happens here is essentially this chlorine free radical attacks this hydrogen and the carbon hydrogen bond breaks in a homolytic fission. As a result, one of the byproducts would be HCl and the other one will be this ethane free radical. Okay, I can say ethyl free radical. Okay. Now this ethyl free radical will attack a chlorine molecule and snatch away a chlorine from this. So I can just write it in this way. This is the radical. This is the chlorine molecule. So this will attack this chlorine. This bond breaks in a homolytic fission. As a result, you'll have chloroethane as one of the products. Cl here. And you have chlorine free radical. Okay. These are your propagation steps. Now for the termination step. Termination step is two free radicals should collide with each other, right? So easiest one is two chlorine free radical, right? Will collide with each other to form the Cl2 molecule again. So that's your termination step. The overall reaction for the synthesis of ethyl ethanoate from ethane is given by this reaction. To find the enthalpy change of this reaction using section 12. Section 12 of the data booklet gives you the bond enthalpies. If you just go here, there's the bond enthalpies, right? And we have to take values from here, basically. So before that, we need to know the structures. 2C2H6. C2H6 looks like this. Correct. So you have to break all the bonds on the reactant side, form all the bonds on the product side. So if I just make a list of the bonds broken, I will have two CC bonds. One CC bond is present in C2H6, right? In two molecules of ethane, you'll have two CC bonds, right? Then you in one C2H6 molecule, you have six CH bonds. So you'll have 12. The 12 CH bonds. Okay. Then you'll have Cl2, so one ClCl bond. You'll have 3 by 2 O2. So 3 by 2 O double bond O bonds. Okay. You have these four different bonds. So summation of bonds broken. This will be 2 times CC bond enthalpy is 346. CH bond enthalpy is, oh, sorry. CH is 414. Okay. And then Cl2. ClCl bond enthalpy is 242. And O double bond O, right? I think this should be, yeah, 498. If I add everything up, I'll get 6649. This is the total energy required to break the bonds. Yeah. And then we need to find the list of the bonds formed. Okay. Now, ethyl ethanoate, if I just draw the structure again, it looks like this. I'll just draw it here. ethanoate. So ethyl will be this part, CH2, CH3. This is ethyl ethanoate. Okay. So again, if I want to find the bonds formed, so there are two CC bonds in C4H8O2, this one and this one. So 2 times CC. Second, you have eight CH bonds. Yeah. And then you have two C single bondo. So this is C single bondo, this is C single bondo. Yeah. Then you have one C double bondo. Is this one basically? Other than this, you have like two HCl molecules. So 2 times HCl. And then you have H2O, so 2 times OH. So summation of bonds formed, we have to find this. So CC is 346, so 2 times 346. CH is 414, so 8 times 414. C single bond O, CO is 358. So it will be 2 times 358. And then you have a C double bond O. C double bond O would be 804. 1 times 804 plus HCl, HCl is 431. 2 times 431 plus OH. We have to find that. OH is 463. Yeah. And if I put all of this in a calculator, I'll get 7132. So delta H will be summation of bonds broken minus summation of bonds formed. So 6349 minus 7312. This will give you minus 663 kilojoules per mole, which is the answer to part 1. Done. Next, one students used bond enthalpy data and correctly calculated the enthalpy change for the reaction as 0 kilojoules per mole. Another student used Hess law and correctly calculated the enthalpy change as negative 4 kilojoules per mole. Explain how the students can carry out a calculation for the same reaction and obtain two different results when calculations are correct. Because the bond enthalpy calculations are the average bond enthalpy values from gaseous species, while Hess law uses standard enthalpy of formation, right? So if the bond types are exactly the same on reactants and products, right? What happens is the net enthalpy change will be 0. So that's why the first student got 0, because exactly the same bonds are present. Yeah. So I'll just write it down. Calculations use average bond enthalpy values, gaseous species, Hess's law uses standard enthalpy of formation substances in their actual states. Now, as I was saying, if the bond types are same, then only your enthalpy will be 0. Okay, so it's not like relevant here, but I'll just make a note here. If the bond types are same in both products, the enthalpy change using bond enthalpy will be 0. Next, we have to find the atom economy. Yeah. So molar mass of the desired product. So ethyl ethanoate, you are synthesizing ethyl ethanoate. So this is the desired product, right? C4H8O2. Find the molar mass, C 4 times 12 plus 8 times 1 plus 2 times 16. Yeah. Divided by the total molar mass of all the products, right? So this thing, if I just find it using a calculator, it's 48, 56, 56 plus 32, 88. This is 88, this is 36.5, and water is 18. So instead of this, I can just use 88 divided by 88 is 2 times 36.5 because you have 2 HCl is 18 times 100, which should give us 49.2%. Now the last question. It's a pretty short question here. The reaction is given, we have to find the equilibrium constant. Equilibrium constant would be product over reactants. This times H2O divided by C2H6O and C2H4O2. This would be the equilibrium constant. 0.6 moles of each of ethanol and ethanoic acid reacted in the presence of acid catalyst. At equilibrium, 0.2 moles of ethanoic acid remained in the reaction mixture. We have to find the amounts of ethyl ethanoate and water, ethanol, ethyl ethanoate, and water at equilibrium. Okay. If I just write the reaction, H2O, yeah. Initial, you have 0.6, 0.600. Let's say X moles of these reacted, X moles of these formed, right? If at equilibrium, you'll have 0.6 minus X, 0.6 minus X. These will just be X, yeah. Now, at equilibrium, you have 0.2 moles of ethanoic acid. So this 0.6 minus X. So C2H4O2, this should be 0.2. So 0.6 minus X is 0.2. So X should be 0.4. Yeah. So moles of ethanol, I'll just list it out. Moles of ethanol will be 0.6 minus X, 0.2. Moles of ethanoic acid will just be X, 0.4. Moles of H2O, again, just be X, so 0.4. That's it. Next, we have to explain the effect of reducing temperature on the value of equilibrium constant. Okay. So basically, you have to the equilibrium constant will only change if we change the temperature, right? So here, if you reduce the temperature, what happens? The reaction will try to generate more heat. Yeah. So it will shift in the forward direction because forward direction heat is released. If it goes to the forward direction, the equilibrium constant value will increase. Right. So basically, the reaction has to increase temperature by favoring the forward reaction and producing as shifts in the forward direction. The equilibrium constant value increases, or the value of increases. So that's it. Yeah. So moving on to the last set of questions. Here's the Maxwell-Boltzmann energy distribution for this curve. Label the activation energy without a catalyst. So we have decreased the temperature, right? Oh, wait, 1 second. We have reduced the temperature. Okay. No, 1 second. It says 60 degrees. So I'll just write it for this one first. At 60 degrees, it's a higher temperature. Yeah. So it'll be a little flatter curve. It'll go like this. So this is the activation energy. of the catalyzed reactions. Okay. This is the activation energy of the uncatalyzed reaction. This is at 60 degrees Celsius. Okay, sketch and label the second Maxwell-Boltzmann curve at the same reaction at room temperature. Room temperature means the temperature is lower, so the peak will be higher, like this. And just go below this curve, like this. And that's it for this paper. Thank you so much for watching this video, and I'll see you all in the next one. Bye bye.